Hey everybody, lesson 3 today, looking at the first derivative test and how that's related is going to help us with increasing and decreasing functions and putting some vocabulary to that. We can use derivatives to classify extrema like we saw in the last lesson, and when we focus on analyzing functions, we can determine or find some predictable behavior for functions through this journey of calculus. We've got an exploration here that leads to the conditions and outcomes of the first derivative test. So we want to use the graph of the function f to answer the questions that are below. And they're telling us to use a red pencil and circle all the points that are corresponding to the local maxima of the function. And I'm getting that information off of here. So we use a red pencil to circle all the corresponding parts. So this would be a maximum, and this would be a maximum. And state those x values. So that would be at x equals a is one of the locations, and at x equals d. Then letter B says that each maximum value f changes from what to what. So looking back at that picture, at this x value, at this maximum value, the function changes from increasing to decreasing, from increasing to decreasing. So we're changing from increasing to decreasing at that maximum value. And at that maximum value, the derivative or the rate, the derivative at that point changes from, well, this derivative is positive on the left and negative slopes on the right. So that rate is a positive rate and then a negative rate. So we have the vocabulary that goes along with maximums. The derivative changes from positive to negative. Next, in number 2, they're telling us to use a blue pencil and circle all the points that correspond to the local minimum and state the x values where that minimum occurs. So getting rid of these little tangent lines here. Using a blue pencil, the minimums would occur here, and that's about it. So at letter C, we have a minimum at x equals c. And what's the behavior there? At each minimum value, the function changes from decreasing to increasing, and the slopes or the derivatives change from negative to positive. So we can say that, nope. Oh, went too far. They change from decreasing to increasing at the minimum. The y values change, or the function behavior changes, I should say, from decreasing to increasing. And at each of those minimum values, the derivative changes from negative to positive. So if you think about it, I have derivatives that are negative, derivatives that are positive. This is a minimum value. We're decreasing to increasing. And at each relative local extreme value, on the function, the derivative f prime is either going to be 0 or it's going to be undefined, like on the corner or the cusp. And we'll go back and look at that in our picture here. So here my slope is 0 here, and f prime doesn't exist here. So no derivative at a corner or a cusp. Then in part C, letter 4, number 4, we're going to use a green colored pencil and sketch a tangent line at the following points and determine their sign. So at point B, we want the derivative at point B with a green pencil. At point B, the derivative looks like, the tangent line looks like it's a negative. And the other one was at point D. We had does not exist. And then at point E, it looks like the derivative is a zero slope there. So at point B, f prime is negative. And if we described the change in the behavior of the graph of the function at that value, I would say the graph is going from concave down to concave up. And at point D, the f prime of D we said was undefined. That was a corner or a cusp. And we could say that f is going from increasing to decreasing. From increasing to decreasing. And at point E, the derivative was zero, and the graph was concave up, and then it changed to concave down. Then letter D, of these 3 points, which two are points of inflection? Well, let's go back and look at the graph. So we have a point of inflection where we were concave down to concave up. So this would, letter B would be a point of inflection. And then same thing at letter E. So B is a point of inflection and E is a point of inflection. Concave down, concave up, concave up, concave down. Oh, went too far, went too far. So that would be at x equals E and at x equals B. And then number 5, if a function f has a relative extreme at a point, then the derivative at the point is either 0 or undefined. Is the converse also true? Well, let's see. I would say no, the converse is not true. At what points justifies your answer? I'm thinking about looking at point at E. The derivative is 0, but point E is not an extreme. It's not an extrema of the function. And we can go back and look at that. You see? So I had a horizontal tangent line right here, but the graph went from concave up to concave down, but it was smoothly decreasing over the interval between D and F. So I had a derivative that was 0, and it was not a relative extreme value. It wasn't an extrema, a relative max or a relative min, like it is at point A or point C. I had a maximum at A and a minimum at C, but I had a 0 tangent line at E, and it was not a max or a min at point E. So the converse is not true. Here's some definitions for increasing and decreasing, and we can read this mathematical sentence this way. A function f is increasing on an interval if for any two x values, the first one and the second one, in that interval, if the first one is smaller than the second one, that implies the y value on the first one is going to be smaller than the y value on the second one. And we can do the same thing in reverse for a decreasing function as well. Here in example 2, we have the graph of a function. It's a piecewise function, and it's defined on -3 to 7. And we want to list the open intervals over which the function is increasing, decreasing, or constant. So the function is increasing on the interval from -3 to -1. This is -3. So it's increasing there. It's constant between -1 and +2. And then it's decreasing from +2 over to +7. So a function is said to be monotonic if its first derivative does not change sign. So if you got a first derivative that's positive all the way through an interval, then I can say that that function is monotonic. It's increasing everywhere. How can we find the values of x on the graph of a function where it's increasing, decreasing, or constant? Some important ideas come to mind here. If a function is a continuous function, then the derivative can only change signs at a critical value. And if a function is a discontinuous function, then the derivative could change signs at a critical value or at a discontinuity where the derivative would not exist. So here's a little procedure. I'm not going to read all of this to you. You can do that on your own time, but we'll kind of model the procedure here by some practical examples. So first, in example 3, we want to find the open interval on this cubic polynomial where that function is increasing or decreasing and justify how we know that. So one thing we would want to do if you're into the procedure is find the derivative, because we need the critical numbers, and we'll use those critical numbers because things change at critical numbers. So factoring out of 2, we have x squared minus x minus 2, and we want a critical number, so we set the derivative equal to 0. And then factoring that polynomial, can divide out the 2. We see we have critical numbers at 2 and at -1. So I'm going to take these critical values, these are my critical points or critical numbers, and I'm going to use those critical numbers in a sign chart. And that'll kind of help me keep my brain organized for the behavior, what's happening on that function, on its domain. So let's say we record the function behavior here and the derivative behavior on the top line. So one thing I know is at my critical numbers, my derivative is 0 at both of those critical numbers. And I'm going to think about this line right here. If I test a number in there, I could test a number on this piece of the domain, and let's say we thought about x being -2. So I'm going to think about if x is -2, what's happening here? A -2 minus 2 gives me a negative number, a -4, and a -2 plus a 1 gives me a negative number, and a negative times a negative makes this interval on the domain, that little subsection, makes that entire interval positive. So the derivative is positive from -infinity up to -1. That tells us that the function is increasing. So these are my little symbolic vocabulary. Plus is positive, an arrow up means increasing. Now what happens if I try a number between -1 and 2? Let's say we try out 0. So if you substitute 0 back here in the derivative, remember this is my derivative, I've got a -2 times a +1. So this part of the domain, the derivative is a negative in that region, and that tells me the function decreases. And then finally, if we test out 3 in this part of the domain, then 3 minus 2 and 3 plus 1 is a positive times a positive, which tells me the derivative from 2 to infinity is positive and the function is increasing there. So that's my little procedure. I find the derivative, get the critical numbers, set up a sign chart for the critical numbers, test values in each section of the sign chart, and then I can give you the information you need. I know the function increases in 2 places, and those 2 places are from negative infinity to negative 1 and from 2 to infinity. And I can also give you a reason for that, and the reason is that the derivative is positive. So where the derivative is positive, the function increases. And I can also say that the function decreases in the other interval, that would be between negative 1 and positive 2, and the reason for that is because the derivative in that portion of the domain is negative. So when we're presented with a continuous function, knowing that the sign of the derivative changes at some critical number, as well as knowing how the sign changes, that's going to give us insight into the existence of whether we have an extreme or not. So if you go back and look at that, you can kind of see the graph. Let me change colors here. See the behavior of the graph? Increasing to 0, decreasing to 0, increasing to 0. At 2, this is a minimum. And at negative 1, this would be a maximum. And the justification or reasoning would be the derivative is 0 at the critical number, and the graph changed from positive or from increasing to decreasing, and likewise from decreasing to increasing. Or the derivative changed from positive to negative, or negative to positive. And how to use the first derivative test. This is what I just said. So again, without spending a lot of time, we can go look at the practical side. So if the derivative changes from negative to positive at that critical number, then C is a minimum, because at C the derivative is 0. If the derivative changes from positive to negative, then this is a maximum, where the derivative is 0, and the derivative changed from positive to negative. If the derivative doesn't change signs at C, then there's neither a max or a min, but you can tell that concavity changed. That's going to be tomorrow's lesson with the second derivative test. Right? Concave down to concave up. This is going to be known as a point of inflection. But we'll talk about that in the next lesson. Now, this is my favorite little cheat sheet or mnemonic, if you want to call it. If we explore how to find points of inflection and intervals where a function is concave up, concave down in the next lesson. But this chart's going to be helpful for summarizing how to use the right vocabulary or recognize what you're doing as you're finding behavior on functions and how you can use it to justify. So if I knew that a function's the derivative was positive, then right underneath positive derivatives, I could see the behavior of the function. So the function has to increase when the derivative is positive. You see how they go with the vocabulary and they line up? It's a great tool to know. And we'll have, if the derivative graph increases, then the function's concave up. And like I said, we'll talk about second derivative and points of inflection tomorrow. So here's example 4. We've got a 4th degree polynomial, and we want to find the open intervals where the function increases or decreases. We want to justify that, and then determine the x values if we have any local extrema. So first, like the last example, find the derivative, 4x cubed minus 16x. Set the derivative equal to 0. Solve for the critical numbers. And use these critical numbers to create a sign chart. So my sign chart, again, is going to be divided by -2, 0, and +2. And I want the behavior of the derivative on the top part and the behavior of the function on the bottom part, because I know the derivative is 0 at these 3 critical numbers. And then I'm just going to test some numbers. So I like to look at this part. It's easiest to substitute into that factored form. So if we substituted a -3 here and a -3 here and did all of that arithmetic, we would end up with a negative number. In here, if I tried a -1 here, I've got a negative times a negative, so this is positive in this section. And if we tried a +1, I got a positive times a negative, so that's a negative. And then finally over here, if I put a 3 in there and a 3 in there, that's going to be a positive derivative. So what's our function doing? Decreasing, increasing, decreasing, increasing. There's a minimum, here's a maximum, here's a minimum. So for part B, to determine the x values of the extrema, we know that, oh wait, don't we have to justify the, okay, so part A, first of all, part A. F of x increases where the derivative is positive. So where does that happen? Between -2 and 0. And between 2 and infinity. So on -2, 0, and 2 to infinity. So that's the first little thing. This is for part A. The function decreases where the derivative is negative. And where does that happen? From -infinity up to -2 and on 0 to 2. And then for part B, the maximum occurs at 0. We have a maximum at x equals 0 because f prime of x changes signs from positive to negative. F prime of x changes sign from positive to negative at 0. And then the maximum, that takes care of that. Then we got 2 minimums at -2 and +2. So we have 2 relative minimums, and those are at -2 and at +2. And the reason or the justification is that the derivative changes signs from negative to positive at that place. Now that's pretty easy. From negative to positive. You got it? Then example 5, we're going to look at some graphic approaches here. For each statement below, let's see what this is about. Sketch a function that represents the results of the first derivative test for a continuous function with a critical number at C. So f has an absolute minimum at C because the derivative changes sign from negative to positive at C. So we could think about this. We could say at C we've got a 0 tangent line, and the derivative is going to change from negative to positive. This has to be an absolute min here, right? Absolute min. So what would the function do? If this is what the derivative does, the function has to decrease and then increase. So I could draw some kind of a graph, I don't know, absolute minimum, something like that. So I have an absolute minimum at C because the derivative changed from negative to positive at that place. And letter B says f of x has an absolute maximum at C because the derivative changes from positive to negative at C. So that's easy. That's the same thing, only different, right? So right here at C, the derivative changed from positive to negative. These are pretty easy. F of x has no relative extrema at C because the derivative is positive for all of the x's greater than 0, and it's strictly monotonic, right? Okay. So that means to be strictly monotonic, I could be something like always increasing. You with me? Always increasing. The derivative's positive on the left side of C, and it's positive on the right side of C. No relative extrema. Then the last one, since the derivative is negative immediately on either side of C, the function has neither a local maximum nor a local minimum at C. So I could do something that had maybe concavity changed. It was concave up on this side, concave down on this side, but the derivatives immediately to the left were negative and negative. How easy is that? Just reading the language and sketching the curves. So here's a little more complicated one. Find the exact values of any extrema on this half x minus sine x for the interval 0 to 2 pi. So again, we want the derivative, which is 1/2 minus cosine. And if we solve for the critical numbers, where's cosine 1/2? And we saw this yesterday at pi over 3 and 5 pi over 3. And then I've got a derivative test strip. And we're going to start at 0 and we're going to stop at 2 pi. But we're breaking up that interval at the two critical numbers, pi over 3 and 5 pi over 3. Now the trig ones get a little more complicated because you have to think about stuff, right? So we're going to test a number. This is my derivative, on the top, and the function on the bottom. So what's the derivative doing? If I substitute pi over 4 in here, so cosine at pi over 4 is about square root of 2 over 2, and 1/2 is 0.5, and square root of 2 over 2 is 0.707, so 0.5 minus 0.7 is a negative. We could do, let's see, pi over 3 and 5 pi over 3, so we could say pi over 2. So cosine at pi over 2 is 0, and 1/2 minus 0 is positive. And then picking a value in here, we're going to get a negative. So we have behavior of the function decreasing, increasing, and decreasing. And that tells us we have a minimum at pi over 3 and a maximum at 5 pi over 3. So to answer our question, we know that G has a relative min, and I think I got to get my calculator out here. Or maybe we can do this at pi over 3. So a half minus the cosine of pi over 3, that's radical 3 over 2, right? Oh wait, we got to plug it back in here. 1/2 times pi over 3, so that's pi over 6 minus the sine, messing myself up here. I need the y value on the G graph. The G graph is up here. Y'all don't let me mess up. At pi over 3, so we got a relative minimum at pi over 3 and the sine of pi over 3. So think about the unit circle at pi over 3. That's short on x and tall on y. So pi over 6 minus root 3 over 2. Okay? Get rid of all that. So our relative minimum value is pi over 6 minus radical 3 over 2. That's one number. That's my y number. And that happens at pi over 3. And the reason that happens is because the derivative on G changed signs. I'm going to abbreviate from positive to negative at that place. And then G has a relative maximum at 5 pi over 3. And same thing, we got to put 5 pi over 3 here, so that value is going to be 5 pi over 6, and it's going to be 5 pi over 3, so that's negative, negative, so plus square root of 3 over 2. And that happens at 5 pi over 3. And the reason is the same as the other reason, just backwards, because the derivative changes signs from negative to positive at this x value. So I got a little reminder down here. Be sure you answer the question that you're being asked. Are you looking for extrema? That's y values. Or are you looking for the location where the extrema occurs? That's x values. Just be sure you know what you're answering. Okay, 3 more little examples and then we're done. So let's find the relative extrema of this. I must have a graph here. Let's look at this. Oh yeah, so it's got a cusp at -2 and +2. So we want to find the derivative, which is going to be 2/3 x squared minus 4 to the -1/3 power, and then chain rule, multiply by 2x. So derivative, when you clean all of that up, 2 times 2x gives me 4x in the numerator and 3 times the cube root of x squared minus 4 in the denominator. So here's what we know. We know that 4x equals 0. So the numerator is 0 at 0. But the denominator can't be 0, which means we have a derivative that doesn't exist at 2 and -2, and that's what we saw in the graph picture. So we got a cusp at -2 and +2, and a 0 tangent line at 0. You see how that works? So if we set up a test strip, these are my critical numbers over here, 3 critical numbers. So we're going to set up a test strip and divide it up with -2, 0, and +2. The function, the derivative, and the function behavior, just to save time, I know this is does not exist, this is 0, this is does not exist. I'm going to tell you that we can tell by looking at the graph, negative, positive, negative, positive. Instead of substituting numbers, I'm thinking about what I saw in the graph. Negative derivative, positive derivative, negative derivative, positive derivative, based on the function behavior, right? Uh-oh, uh-oh, I lost my way there. And the function was decreasing, increasing, decreasing, increasing. So this is a minimum, 0 is a maximum, and 2 is a minimum. And then we can state it out this way. We got f has a relative max, and if you substitute back into the function at -2, oh, a max was at 0, right? We got 0, that's 4 to the -4 to the 2/3. So we got the cube root of 16, because I'm thinking -4 to the 2/3 power. So 4 squared, that's 16, and then the cube root. Doing math in my head, don't let me make a mistake. Or if you wanted to simplify that, you could say it's 2 cube roots of 2. And that happens when x was 0 because f prime changed from, and I'm going to abbreviate again, from positive to negative there. Okay? And then we have a relative minimum. And same thing, we got to plug in for our minimum. That would be at the other 2 numbers. F has a relative min. And if you plug in a 0 back here, oh wait, we were plugging in, I'm sorry, we were plugging in 0 for the first one. We're going to plug in a 2. So we got 0 to the 2/3. So that's going to make our minimum 0. And that happens when either x is -2 or +2. And the reason that happens is because f prime changes from negative to positive. Okay? So 2 more to go. In example 8, find the x-coordinate of the relative extrema. So this time we're finding just the x-coordinate. That's our critical number, right? Off of our test strip. So mercy me, look at this. H of x is x to the 2/3 times x minus 2. So we got a chain rule. We could say this is x to the mercy. Should we put that together? 2/3, 1 and 2/3. So 5/3 minus 2x to the 2/3. I guess we could do it that way. We got, I don't know if that would be faster or not. Give me a minute to work on something here. I think we'll just do the product rule. So we got first derivative times derivative of the second plus the second times the derivative of the first. Back that up. That was the other problem. I'm looking at the wrong work on my paper. I need this one. So the first one, 2/3 x to the negative 1/3. Hold the second one constant. And then x to the 2/3. And take the derivative of the second one. That's a 1. Yeah, that way we'll have a common denominator and stuff. So we got 2 over 3x to the 1/3, and this x minus 2, and I need this to have a 1/3 x to the 1/3, so that's going to be a plus 3x, right? To get that common denominator, I need a form of 1. Now, this is 2x minus 4 and 3x, so 2x and 3x gives us 5x minus 4 over 3x to the 1/3 power. And my critical numbers are 4/5 and 0. Here the derivative is 0. Here the derivative doesn't exist. So looking at the test strip, the derivative is going to be positive, negative, and positive. The function would be increasing, decreasing, and increasing. And remember, I'm plugging back into this part of the derivative for numbers in each of those intervals. And I want the x values. So at x equals 0, there's a relative maximum. And at x equals 4/5, where the derivative was 0, there's a relative minimum. Here the derivative didn't exist, and here the derivative was 0. And then our last example, this was a lot of examples. Given this rational function, find the intervals of increase, decrease, and find the coordinates of the extrema. So g prime is going to be denominator times derivative of the numerator minus numerator times derivative of the denominator all over the denominator squared. And that cleans up to be x squared. This is going to give us x squared minus 4x plus 3. And we can factor that as x minus 3 times x minus 1 over x minus 2 squared. So we know what our critical numbers are. We have a critical number at 1, and another one at 2, and another one at 3, because here we have vertical break and 2, 0, so derivative doesn't exist at 2, and it's 0 at 1 and 3. And just to save time, I'm going to tell you what my work turned out to be by substituting values in for this derivative. And they want us to give increase and decrease. So we can say that g is increasing on negative infinity to 1 and on 3 to infinity because the derivative is positive there. And we know that g decreases on the other intervals from 1 to 2 and from 2 to 3. And the reason is the derivative is negative there. And then the second part, we have a relative maximum. And they want x coordinates this time at x equals 1. And the reason was the derivative changes from positive to negative. And then there's a relative min that happens at 3. And the reason for that is the derivative changes from negative to positive. So first derivative test. This is a great tool. And that's an end to that one. And I'll see you next time for second derivative test. Bye.